like to welcome everyone to our seminar series at the University of San Francisco. The seminar series is sponsored by the Data Institute, the umbrella organization of all things data science at the University of San Francisco. Our speaker today is Nicolas Thiebaut from Roblox. He is a senior machine learning engineer who also teaches for our data engineering extension program for the ML Ops course. He has been in the data realm for over 8 years, working in both Paris and now living in San Francisco. Today he's going to talk about large language models and practical aspects of building large language models. Can we give him a round of applause?
Thank you, Nico. Thank you, everyone. Please let me know if you don't hear me well, or as you can hear, English is not my first language, so if I don't enunciate well, you can also let me know. I'm really happy to be here today. There's a lot of people. I'm going to talk about a subject that I really like, and I hope that you'll be interested too. It's a subject that is hard to avoid these days. So, yeah, as people say, I'm Nicolas, Nico, and I work for Roblox. This is my full-time job. It's a gaming company in San Mateo. And I focus mainly these days on something related to what I'm going to talk about today, which is how to create non-player characters in games that are more interesting, more engaging, and more autonomous. I want to thank the whole Masters team for first welcoming me to the team a few months ago, giving me the opportunity to create an entirely new course on a new topic that I hope went well. I don't know if there's anyone who took the class. I don't see anyone right now. There might be a few of you. And yeah, I want to thank Diane, Victor, Alain for this opportunity to teach and this opportunity to talk to you today. I hope that this presentation will be as interactive as possible. The more questions, the more comments, the more dissenting parts, the better for me and for you. So don't hesitate to interrupt me, raise your hand or anything. And yeah, let's dive into it. Language agents, what is it? That's what I'll introduce you to first. So it's an emerging topic. So as an emerging topic, everything is fuzzy. Definitions, what it is, what falls into the umbrella of language agents. So for this reason, I'll start with examples so that at least we can anchor our imagination on something concrete. You're probably familiar with some of these examples for sure, but I just want to be sure that I expose you to the whole landscape of applications. I'd like to talk to you about something that took me a little while to figure out, which is those things like ChatGPT and other agents that I introduced. Like now they started interacting with the world, like they can search Bing. Some of them, they can have a memory from which they can retrieve things when needed. They can also take actions, like you'll see that nowadays there's robots that are powered by large language models, and the question is how do you actually go from language, English, into coding actions for a robot? I want to talk about that soon. And then I'll introduce you to more practical aspects, what is nowadays toolbox for those topics. Of course, it's evolving fast, but it's interesting to focus on what are the patterns that are emerging to build applications that are using large language models for autonomous behavior. And then we'll talk about an emerging topic that people call LLM ops, which is, large language model operations. How do you actually deploy those models? How do you monitor them in production? How do you debug them and whatnot? But the presentation is going to be flexible. I probably have too much content, if anything, so I'm happy to start and discuss some topics more in depth and to skip others, depending on your interest. So I'll try to read the room and see how interested you are. But first, probably the funniest part, example. I don't know if you're familiar with this one. This one is fairly popular. It's a project called AutoGPT. And interestingly, it's something that probably a few years ago would have been coming out of academia, and it's one of those new types of projects where it's just a collective of people driven by mostly one person, but still a group now with a Discord chat, and they're building something, and they don't publish papers, but they're building something that is kind of getting edge. I want to show you what we're talking about. So here they have a video in their repo that is going to be hard to follow for you, so I'll comment because it's pretty small. The interface is pretty bare, as you can see. But the example they share is, this is this generic agent to which you can assign a task. Here the task is pretty simple. On the right-hand side, you can see that the goal, the role is to teach the user about AutoGPT. So it's something you could do with ChatGPT. But if you want the full complexity of this, you actually have to search internet. So if I go back to the beginning, the input of the user, I know it's a bit hard to see, is that AutoGPT has to be an AI designed to teach me about AutoGPT, so about itself. And then it's going to define a subset of tasks, the first one being search AutoGPT, so search on the internet, then find the GitHub repo, so it's going to actually parse the code to explain what AutoGPT is, and then terminate. So here there's planning already, something that we'll talk about later. Establishing a plan and then executing it. And then there's another thing that is thoughts. So thoughts like, I think the first step should be to use the Google command to execute the first goal. And then there's a whole plan, there's criticisms, and under the hood, of course, there's programmatic access to Google. There's going to be a lot. Honestly, the goal is probably not to read everything that is happening, but you just have to know that a plan, a high-level plan was devised by AutoGPT using large language models. It was refined, and then every sub-goal is broken down into smaller goals. And you have comments on the left. You can see what AutoGPT is doing. So here it's ingesting the entire repo of AutoGPT itself. Summarization takes time, so it summarizes it, it probably stores it in a long-term database under the hood. Then there's more reasoning, there's refined plan, there's criticisms of the plan. So it's a lot of explicit reasoning steps. And it's probably going to be end of it pretty soon. Okay. And I think the final distraction that it got after parsing the code, searching Google and whatnot is here. AutoGPT is an experimental open source application that uses GPT-4, blah, blah. So the task itself is not the most interesting in itself, but it's an example of what complex behavior can be. And here you have two important components of every language agent, which is first planning and reasoning, and second access to tools. The tools here being just Google search and GitHub. So that's my first example. Sorry, I'm going to have to scroll back all the way up. I probably clicked something wrong. Here. A second example that I like that is also fairly recent. So AutoGPT I think started earlier this year, which is like a lifetime in that field nowadays. There's a more recent work from NVIDIA and a couple of colleges that is called Voyager. That is very interesting. Here we enter the realm of gaming, playing Minecraft. Minecraft, you can interact with it through a JavaScript framework that lets you basically parse the state of the world, so know what is around you as an agent powered by machine learning, and take actions. And some people have written a program with the goal of creating a diamond. So I haven't played Minecraft, but apparently creating a diamond in Minecraft is fairly elaborate because there's a whole set of tools that you have to build, and then you have to fight enemies to find materials to build more elaborate tools and so on. And the diamond is kind of the pinnacle of this technology evolution. And so in a nutshell, complex task, there's a JavaScript framework that tells you what is the state of the world, what is around you in a structured way, and then you can take actions. And what they did, that seems to be emerging as a potential pattern for complex autonomous behavior in games, but not only, is to create a skill library. So they ask a large language model, okay, what is your plan first? Okay, my plan to create a diamond is that first I will have to build that and this and that. Okay, so that means that first maybe you have to craft, I don't know, an axe. And for that, it's going to further refine into what is needed to craft an axe. And in order to perform these actions, the one in the middle that is illustrated that maybe you don't see because it's too small is fight a zombie. Probably you have to kill zombies on your way. They actually have the large language model write the code to fight the zombie, which is something like, okay, pick the sword in your inventory, then pick your shield apparently, and then start fighting or something like that. And they write the code, so they generate the code. Then they execute the code. If the outcome of this is something valuable towards the short-term goal, they add that as a new skill in the skill library alongside with the code that executes it. So they describe it, they have the code together with it that can execute that, and then they iterate. Now they have a skill that is fighting zombies. They're going to use that, and then they're going to create higher level pieces of code like fight a crowd of zombies. Maybe later on they'll see 3 zombies and it's different to fight 3 zombies than 1. They're going to write the code that uses the skills that they defined before to craft more and more complex skills as time goes by, all the way up to crafting a diamond. So here we have generating code, validating it in an environment. This environment is Minecraft here, but you can easily think about the potential extensions. That could be a robot, that could be parts in a factory that are automatically building something. And it might be emerging as a new pattern. Craft code, log it as skills that you're going to reuse later, and combine them. Voyager. The third example, that is probably the one I like the most, is recent work from April this year from the University of Stanford called generative agents. So if you Google it these days, you'll find a lot of things because it's making quite a bit of noise. What they did here is try to just simulate a small human society. So they created a sandbox environment with a nice game interface as well, where they have agents, 25 of them, that are bootstrapped with goals and personalities. So basically they write the prompt for a large language model telling, okay, you are James, this is your job, this person is your wife, and this is your first day you wake up. They do that for 25 agents. And what they observe is very interesting. They ran the simulations for 2 days. So those agents, they actually talk to each other. They perform actions in the world, because the world now has actions that are encoded and available to the users, and has a state, like the door can be open or closed, and the agents can open or close the door. They run the simulation for 2 days with millions of calls to OpenAI GPT-4. And what they see is very interesting. They see emerging behavior. And the one that they cite in the paper the most is that they basically nudged one character by chatting with it into organizing a Valentine's Day party. Just one character is aware of that. And what they observe is that there's been information propagation in the community. And next thing you know, a few days later, there was a Valentine's Day party. Half of the characters showed up. There were some dates. Some of them failed, some of them succeeded. And this is all emergent. And the way they did that, to show you a little bit what's behind the curtain, it might be a bit small as well. But in a nutshell, they just have a prompt that describes the character. Okay, this is going to be your generic context. They made sure manually that the relationships between the characters that they were defining were reciprocal. Like if James is married to Mary, then Mary is also married to James. So there was a lot of hand engineering, basically, handcrafting. And they equipped, importantly, those characters with a memory stream that is very large. They log everything that happens. Oh, I ran into Bob this morning, or I closed the door, everything. A very large memory stream that logs everything in plain text. And they equip those agents with a reflection piece. So at the end of the day, they actually reflect on events of the day, and they reorganize their memory. So, I don't know, maybe dreaming, maybe one stage of sleep, something like that. But they explicitly reorganize their memory. and they're able to retrieve events from their memory. So if Bobby is starting to narrate, maybe a topic will pop up that will cause the agent to fetch a specific memory and put it in their prompt, and basically the prompt is all of the state. And with this mechanism, just large language models, a simple memory to store logs in plain text, and a reflection mechanism, they observe this emergent behavior. So, very interesting, all digital. And now I have a physical example. Of course, you plug similar things into robots, and then enters RT2. This one is from July, or almost August actually, from DeepMind. And basically what they did is they equipped robots with large language models for planning. And the form it takes is that the large language model they train can generate actions that are very low level, things like translation, rotation, as you can more or less see here basically. And they train the language model, I say language model, it's actually a vision language model, it has access to vision and language to answer questions. And by doing that, they end up being able to tackle very complex tasks like push the ketchup to the blue cube. You have ketchup here. Ketchup has never, this type of ketchup has never been in the training set. This is a fairly clean validation strategy. And you have the arm with just these basic actions of translation, rotation, and potentially grasping, able to move the ketchup to the blue cube right here. So again, agents can perform simulations, interact with the digital world, the internet, the computer, and also you plug that into robots and then you enter the physical brain. So this is pretty cool. It's evolving fast. How to catch up with this is almost impossible, basically. So here's a short timeline of all the main projects in that field of like trying to have the most autonomous agent as possible. And what's interesting is that recently people started trying to organize the field in terms of framework and concepts, because these things have emerged right from people like academia, a bunch of different angles. And I think what's interesting is that it seems like with these agents we're going from the usual paradigm, which is, okay, large language models are used to have an input and then produce an output. That's basically ChatGPT, although with ChatGPT, of course, you have several rounds of interaction, which makes it a bit more elaborate potentially. Then the next step is, okay, how about with language agents? We actually equip them with actions and observations from the world. So I'll talk about what it means later and how it is done, but the basic principle is fairly simple. If you have a program that is calling a large language model and is parsing the output of the large language model, and you tell the large language model that it has access to, let's say, the Wikipedia API, then you can tell it that if it wants to access the Wikipedia API, it should output a string with this form. And then you parse it, you run the search, you give it back to the language model, and you iterate. Same thing with observations. You have programmatic ways to provide feedback from the environment back to the agent. So this is step 2. And step 3, what people started, at least at Princeton, started calling cognitive agents, is the following, that not only you have a large language model that is able to directly interact with the world, but this large language model also has access to an internal memory, which allows it to go beyond the limitation of the prompt, that is a hard limitation, and basically access as much as it wants and store. And you have more and more complex reasoning steps that I'll get into. The planning is getting more and more complex and interesting. It's getting way more complex than just asking the large language model to output the thing that it wants to do. But there are rounds of iterations. So that was a fairly long introduction, probably. Do you have questions or comments? Yes, please.
In the robotics slide, when you were talking about how did an LLM work there? I feel like it's more like object detection or an OCR going on, but how does the LLM do that?
Yeah, thanks for the question. In case some of you didn't hear the question, it's like, okay, robotics example, how is the LLM embedded into this? So I think this diagram is the best. Basically, what they have in the training set when they're training this RT2 model is they have pairs of or triplets of images, questions, and answers. Some of them are just the usual field of visual question answering. That is learning how to predict the right answer giving the pair of a question and an image. So like the first one is what is happening in the image, and there's a donkey, and the answer is that the donkey walks down the street. But they also added to this data set things that are specific to robotics. So the image of the robot that is doing something, and then the question, what should the robot do to push the ketchup, for instance. In their data set, they have the answer to that. And it was probably a lot of work to build the data set that has answer. And the answer, what I'm calling the answer, is in plain text, translation, but the answer will be translation is equal to 0.1 minus 0.20. So you're describing directly like every minute movement that the robot should make. And if you think about it, like be able to generate answers from questions and images, answers in plain text, is not very different from generating this, right? Generating explicit descriptions of movements. It would be the equivalent of just writing down where should the robot walk, and then saying, okay, left and right and straight. It's basically one step further than that, and that's it. I guess, I don't know if that was clear or not. Yes?
I have an assumption that every LLM model uses text, and the input here is read. So is it a combination of object detection and the LLM does not use text? Or am I wrong? You should look at LLM only as text.
So there's also the image, right? There's no explicit image detection here. That could have been an approach, though. Like you could have, but even you can have visual description of scenes. There's people who have done that. Like they take the image, they convert that to text, and you have fairly generic ways of doing that. But I think here your main concern is that, like, how do I go from outputting text to outputting this structure, like, okay, translation, move left, fly, 0.1, and things like this? My first answer is that there's a naive approach that you could have taken, that's just that a number is text. Like you can generate the text that's going to be 0.1, and with LLM they can generate numbers, right? If you ask a math question to ChatGPT, you'll have a number as the output. So even if that was the approach here, that would be possible. They did something slightly more elaborate, that is that these kind of actions are actually specific tokens in the vocabulary of the language model. But it's a bit like, we enter the technicalities of it, but it's possible to go multi-modal with those language models. And the way you do that, like the simplest way, is fairly simple. It's just that instead of saying that you can only have words in your vocabulary, you can say that the inputs and outputs can potentially be something else. And this something else can be image patches. This something else can also be structure of the actions like here. Yeah, you're welcome. Yes?
So right now, if you look at the picture on the right, if you make a command, push the ketchup to the blue cube, then it's going to push the ketchup to the blue cube. But can you do it in a reverse order? So you show this action to the robot, and then it's going to generate the text or some kind of meaning that, so it's going to generate a text that pushes the ketchup to the blue cube, and is that going to be a one-to-one relationship?
Let me clarify this one. The question is like, okay, I guess what is generated, like maybe just describing this, what happens here. So here it's post-deployment. So we train on all those things, and we have a train model that is able to take as input images and instructions or questions, and generate instructions. So this thing, push the ketchup to the blue cube, is the input. The user is telling the robot, okay, you have to do that. And the other input is this image. So the robot is seeing its own arm and the scene, and is given this instruction. And what it's going to generate here, or what the language behind the robot is, the language model is going to generate, is something like this. It's going to generate instructions with translation, rotations, and grabbing. And then you have, I don't know, whatever program is behind the arm, execute these instructions. No?
Up.
Yes.
Okay. So this application seems similar to what reinforcement learning does, right? So in reinforcement learning, usually it takes like a lot of iterations to actually arrive at a certain output. Like in this case, pushing the ketchup to the blue cube. If that was your goal, then in reinforcement learning, you'd have multiple iterations. Would you say that the language agent is like an improvement to reinforcement learning to reduce the number of iterations, or is it only situational?
Yeah, thanks for the question. I guess the question is, okay, what is the relationship between this and reinforcement learning, because the goals are pretty similar. It's actually a comment that I wanted to make and I forgot to make on this, that if you're familiar with reinforcement learning, or at least the basics of it, like this diagram is very similar to the reinforcement learning setting. I guess it's just that with the observations, you would also have rewards explicitly. I think the goals are very similar. There's a lot of people trying to do things that people are trying to do also with reinforcement learning, but that are hard to do. Quite often because the reward is sparse. That means that, I don't know, crafting a diamond in Minecraft is like you only get a reward if you have the diamond. And until then, you're just doing random. It's really hard to learn. So I think there's people trying to replace reinforcement learning with LLM kinds of approaches like this one, like the robot. There's people trying to use LLMs to guide reinforcement learning. There's a paper from today, actually, that I almost wanted to add to the presentation that is trying to craft rewards efficiently for reinforcement learning agents using large language models. And this field is actually, there's not one paper, but several, and it's probably very promising, because if you've done reinforcement learning, you know that the hardest part is to craft the reward, and people in practice spend a lot of time crafting the reward. Crafting the reward meaning, if your end goal is to create a diamond in Minecraft, you probably will never get there with the usual reinforcement learning algorithms if you just tell it that this is the one goal. You have to tell it explicit things like, okay, having an axe or a furnace is actually, you're on track towards your goal. So you get a small reward for that. And so there's high hopes that large language models can actually help with reward shaping for reinforcement learning. And there's also one application that is a synergy between large language models and reinforcement learning that I will talk about, but it seems like could be very powerful to combine both. Yes?
So, as you, based on your explanation, can I just understand that the cognitive language agent in gaming is, so the LLM can, you can leverage LLM to reduce the search space when you do the reinforcement learning, so you can find the reward efficiently. And then
Yeah. So the question, just in case, is: am I saying that you can use large language models to reduce the search space in reinforcement learning, to make reinforcement learning more efficient? I think in that case, I think what you're saying exists, but what I was referring to is a bit different, like in the sense that the search space is the same, like you still have the same actions that are available to you, but the reward is easier to learn, right? It's easier to learn the actions that give you a reward because, again, if the example is that to craft a diamond you need a furnace, reinforcement learning basic approach, you build a furnace, you have no idea that it actually helps. You have no idea that it's an improvement. And so what I'm saying is that there's high hopes for having the LLM say, okay, if you want to build a diamond, you should build a furnace first. And then have the reinforcement learning algorithm learn how to build the third next video. But what you're saying also exists, but it's a little bit more niche, I would say. Niche. Okay, are there more questions? Yes.
Excuse me. So if you look at the diagram B, then you have a sequence of observations, and then that's going to change the values in the nodes, and then based on that value in the nodes, it's going to output an action, and then it's just goes on and on. So if you look at the diagram C, well, so like in that sense, you can think that the numbers in the nodes, that's the accumulation of what happened in the past. So how is that different from the memory in the diagram C and the values that is stored in the node?
Yeah, thanks. That's a great question. So you're saying that in A and B, if you are training the large language model with little nodes, here are the, I guess, more edges that they represent numbers, and with numbers, the values, the collective values of these numbers, they represent the memory. And then reinforcement learning would be okay, or deep reinforcement learning would be the approach where you actually update the those weights based on the reward from the environment. But with language agents, there are most approaches, they don't update any weights. So that's the big paradigm shift in the sense that you keep the weights of the language model the same. There's no gradient descent. Learning is only done through accessing tools and updating your prompt. So your state is not the set of weights anymore. The state is what's in the prompt. And if you have those, it seems like those large language models are becoming powerful enough that if you have the right prompt, you can perform any task. And there's even approaches that formalize the prompt as a state, an abstract one, and do not even produce actual English in there, but just try to produce like the right set of tokens and characters so that the language model is going to be able to perform the task. But I'll elaborate a bit on what it means to learn without gradient descent, but we don't change the weights anywhere. So training in the usual sense is different, I guess. And I'm telling you, when you work like, I don't know, working actively on these topics, it's a weird shift because I used to train models as, I don't know, for a living, and now I'm not training models anymore, so it's a bit different. Are there more questions on just the generic presentation? Okay, I'll try to make the best use of our time because we spent quite a bit of time on this introduction, which is great because this is what we're talking about. And I'll try to skip, and you pause me if you. I'll skip a few things, and you'll pause me if there's anything that catches your eye. I just want to elaborate on one thing that I'd like you to take away from today, in a little bit, which is what does it mean, like, to several things, to use tools. How does it work? The fact that you can access search on Google, that you can access Wikipedia, that you can actually execute code from a large language model, calculator, calendar, everything you can think of. What does it mean to take actions? I alluded to that. What does it mean that you have a memory that you can access when you're deciding on what is going to be your next action? And then how does planning work? This is the interesting part where there's a lot of development. How do you have a program that uses a large language model to plan correctly? I'll probably skip this one. Just know that in order to teach an LLM to use tools, you just need to create conventions. You just need to know what in the output of the large language model is something that should trigger a programmatic action. And you pass the output. It's that simple. There's a famous paper that seems to be the technology behind first a lot of large language models, but also behind how ChatGPT uses plugins, which is called Tool Former. And with the Tool Former approach, they basically fine-tune the language models to learn how to output sequences of strings that look like, it's a very small example, but the tiny pink thing that you see here, okay, bracket, QA, and then a question. And then this is a specific string, right, that you would not find in regular English. And so this is the convention that some of the large language models they adopt to know when they should trigger API calls or actions or whatnot. This one I'll skip because it takes a bit of time to introduce how to do it with fine-tuning, but there's a simpler approach that is without fine-tuning. You can have a large language model that has never written, I don't know, brackets, API call, Google search, but you can just tell it in its prompt that it has access to the API call, that you have to describe the API, you have to tell it that it's something that it can use to search, and then if relevant, you run inference on this large language model, and it's going to output the strings possibly. And if you want, you can show examples. This one is not the most readable, but you can imagine that I can write in the prompt of my large language model, search, colon, what is the nickname of the city of Pittsburgh, and I tell the large language model that this is an example of calling an API, and I show an example where it would be useful to make that call. In the prompt, I give a few examples like this, and then now the large language model will be able to output strings that look like the one I showed. That would be, I don't know, search, what is the University of San Francisco, and boom, it's going to generate this conventional string, and I'm going to parse that and run the search, get the output of the search to the large language model, and ask it to keep going with inference. So you can use tools. After tools, I mentioned memory. There's a big question of, and a big quest towards language models that can fit in as much as possible, that can have the largest context window. So for context, the largest context windows, which is the input of the large language model, nowadays are around 100,000 tokens, which is roughly 80,000 words in English. So it's not too far from a novel, an entire book. So you might think that you're able to cram in a lot. But I think it seems like we're reaching the end of this quest for larger context windows for several reasons. One of them is that there's approaches that do not require writing everything explicitly in the prompt that are working pretty well, using the tools, for instance. Another reason, I will skip this one. Another reason is that there's recent research that has shown that actually if you make the prompt bigger, if you increase the size of the context window, the input to the large language model, the large language model is going to ignore most of what is in the middle. And it's going to focus on the beginning and the end of your input. And so that's a good reason for not trying to just cram everything into your prompt, but start adopting what is called retrieval augmented generation, or RAG, which is basically, okay, how about we store something into memory and we decide at runtime what is the most relevant thing to fetch from the memory, depending on the question of the input. And, I probably forgot to copy one slide, but what you I'll talk about it later. What you can imagine is just that whatever relevant information potentially you want to store, you can just put it in what we call a vector database. So you compute a vector representation of the string. There are many ways to do that. And you add this string together with the corresponding vector to a vector database. And at runtime, there are many techniques to retrieve the most relevant strings using those vectors and add them to the prompt. And the last piece, so I mentioned tools, there's memory, and then there's, okay, how do I do planning? Knowing that I have these tools, knowing that I have access to a memory from which I can fetch things, to which I can write also this memory, and also that I can rewrite potentially and erase things that if I want. So there's a lot of approaches. There's a recent history started actually in 2022 with this paper, Chain of Thought, which is something very simple, but that was the very beginning of that. They basically said, oh, it's interesting, when we talked to ChatGPT, that didn't exist at the time, but large language models, if you just add things like, okay, instead of giving the answer to a question, think step by step. Or even people writing their prompts, take a deep breath. And quite often it helps with reasoning, just those very simple approaches. There's been an evolution of that, which is people came up with React a year ago, which starts looking like a proper planning algorithm using large language models even more, which is the following. You can see an example here. There's a claim, and basically the large language model is asked whether this claim is true or not. If you use regular prompting like chain of thought, you just write the claim and you ask the large language model to think step by step, and then after my hand, everything is generated. And here, the standard approach, chain of thought, gets it wrong. And with React, they started interleaving thoughts, actions, so tools, and observations from the output of those tools. And an example here is there's some form of planning in the sense of thinking what I should do as the large language model, taking an action, searching for this movie on the internet, looking at the output, having a new thought based on the output, etc., etc. So you can iterate as much as you want until the large language model decides that it's going to generate finish, and then the answer, which is refutes in this example. So it doesn't look like rocket science, but there's the idea that maybe you can iterate, right? Iterate with tools, refine, and actually reflect on what you're seeing. The next elaboration of that, I won't spend too much time on this, is to actually have several episodes and potentially a reward from the environment. So here you start really entering the realm of the reinforcement learning setting, especially on the right-hand side here. If you have an environment that can tell you whether you're right or wrong, maybe you can have several episodes. You can have the LLM, for instance, trying to answer a question, and then maybe it's going to get it wrong, and the environment is going to tell you, no, you're wrong. And here there's some form of learning. And you're going to ask the LLM to reflect on its failure, to start a new episode with the reflection in the prompt. So here we start seeing the pattern of just adding something to the prompt or modifying the prompt as learning, because there are several episodes. And of course, this paper has made a lot of noise as well, because they got pretty good results from March this year, reflection. And even more recently, there's been a convergence, so this is August, there's been a convergence of reinforcement learning and language agents. Here they act in synergy, but I probably skip this one and talk about it if you're interested later. Other questions so far? Yes?
You skipped the embedding slide, I guess.
Yeah.
Okay, so were you supposed to talk about?
Yeah, I was, but I knew that I had way too much. I'm happy to spend time on this. So just so that you know the choice that you're making, if you tell me that you want to spend time on this, I was about to talk about the toolbox and more the deployment side of things, which is what is different between deploying regular machine learning apps and LLM apps. But I also have a version where I can do it in one slide and probably less than 5 minutes. So it's hard to read an entire room. So I guess I'm happy to talk a little bit about embeddings. Because I completely skipped this question. I said at some point, okay, maybe when you have memories that are in plain text, you can just store them as a vector. But it's not obvious like what it means that you have text, a vector. What is this vector? And this vector, there's traditional approaches. Some of you might be familiar with the TF-IDF method from information retrieval, or BM25, his older brother or younger brother. So it's not new, the idea that you can store text with vectors, and but recently it has gotten much better, because traditional approaches, they were sparse representations and didn't know anything about semantics. So my example here is that for the usual representations that we had before, which are language models and a little bit before, soccer and football would be completely different, 100% different. So it's the same difference as soccer and tomato. And also, like those representations, they were not using the context. So for instance, Python had one representation, regardless of whether it appeared in a computer science context or in the animal kingdom. And so now what we have is something a bit more abstract, semantic representations, dense ones. And the way they work, they're usually learned in what is called a Siamese setting. So you have a data set of sentences that you consider as similar or dissimilar, and then you train a model to basically learn to produce vectors that are as close as possible for similar examples and as far as possible for dissimilar examples. And at the end of the day, when you run a sentence with those models, basically you end up with a vector. And if you're familiar with, I don't want to get into the weeds, but if you're familiar with the transformer architecture, birth models, GPT, all of that, they always generate a sequence of vectors, one per token, so roughly one per word, a token with like a dimension 1000. And if you want a simple version of what it can mean to store the sentence as a vector, you can just think, okay, I pass my entire sentence through my GPT model, but right before it does its task of generating the next token, you actually extract all of the vectors that is the internal representation of the model, and you say that this is the vector representing the sentence. And you put in your memory the vector and the corresponding sentence. Okay, I see that. So, are there more questions on this or something else? Oh yeah, sorry. Go ahead.
So in one of the slides you have mentioned long memory and short memory. So how are these LLMs engineered to utilize that? Let's say in a chat, I have changed the context or moved to a different topic. And again, in later on queries, I was trying to utilize one of the previous queries response. How are they engineered to utilize short and long? And does this have an effect on the CPU memory utilization?
Okay, so yeah, the question is, okay, what is the difference between short and long-term memory? How does it work? The fact that they can retrieve, the large language models can choose between those and retrieve things from them, and how does it affect the CPU utilization? I think the answer to the second question would depend a lot on the actual implementation. Like, how does it affect the CPU utilization? Yeah, there are so many ways to implement that I think it's hard to answer with a generic answer. But I would say that the simplest version of short-term memory versus long-term memory is your short-term memory is just your prompt. This is like the latest thing that happened. For instance, ChatGPT, you have the entire conversation possibly in your prompt, and this is your short-term memory. The long-term memory would be retrieving the most relevant things from your memory. So for that, you have to have a driver, of course. It's not going to be the LLM directly that is going to fetch from memory. You have to have a program that is looking at the output of your LLM. And if your LLM is generating statements like fetch relevant things from memory, you're going to fetch from memory. This is one approach. And another approach is that in the very beginning of your prompt, like what you don't see when you're calling ChatGPT, for instance, and what is part of the initialization prompt, you can have suggestions that the LLM has access to an external memory, that it should fetch, for instance, the 3 most relevant items from this memory at every time step, so every interaction with the user. And then if you do that, same thing, the large language model is going to generate as part of its output those calls. It's going to tell you, I want to call my external database just by producing the same string that you gave it in the prompt. You gave examples of fetching memories from the database, and it's going to generate it. And then you have your driver, your program that is calling the large language model, that is going to catch it just past the output string, and then execute the retrieval, and then put it back in the prompt.
What happens if we ran out of memory?
If we run out of what?
Memory.
If we run out of memory, I think the first thing you will run out before that is probably prompt, right? That your prompt will be full. So you have, are you thinking on the database side, or if you run out of memory? Well, I think that's what all the companies working on developing vector databases are working on. That they're trying to make it very large scale, and I think it can be very large scale, because it can be distributed, right? You have Elasticsearch, for instance, that has been doing that for years, right? It was not large language models, but storing vectors together with text. It's an old problem for which there are natural technologies, and I'm not an expert. I don't know what's the limit of that, but I know that it can get very large scale. So I don't know if you can store the entire internet, for instance, but probably quite a bit. I have a number actually. I know that, for instance, in one, I had it in a table before, I think. Yeah, I forget what, sorry. But, it's later. Yeah, I don't think it's the major limitation. It's not important. Okay, so it's already 20. So we have 9 more minutes. So I guess the best use of our time is that I talk briefly about something that I think is going to be relevant for you as a takeaway. And then that I open it up for questions if you want, and then after that I'll be around if you want to chat or ask questions or suggest me. The one thing I wanted to mention is first this quote that making something cool with large language models is really easy, but it's really hard to turn that into a production application. One of the reasons is that there's a lot that has changed. This is the one slide on which I wanted to spend 2 minutes. There's a lot that has changed when you're trying to deploy these applications. You can think about it in the following way. You used to train models for a certain task, like, I don't know, what could it be? Language identification, for instance. You used to train a model with label data of input strings, and then what is the language that was used there? It's actually a harder problem than you think in some cases. And let's say now you want to do that with your large language model. With your large language model, hopefully you shouldn't even need training data with explicit labels. And so what's going to be very different is that, you need a lot of data for in ML, in principle, to train a model that is good. With LLMs, it's like you already have the foundational model, so you might need a few examples that possibly you just put into the prompt. Or if you have more examples, you might want to fine-tune the model, and there are efficient ways to fine-tune the model, so here there's still training, but you don't need a lot of data. The other one is evaluation. In the era of generative AI, how do you evaluate the outputs? Right? It's the test set approach can work to a certain extent, but it has limitations. And so there are tons of people thinking about how to have humans in the loop, how to run A/B tests with these kind of tools, but it's pretty hard to evaluate offline. Also the cost, so regular ML, you might spend a lot of money on training, not even sure, but usually serving is fairly cheap. And then LLMs, serving is going to cost you a lot of money, and you might not have to train at all. Finally, latency, so cost and latency go together for sure. In regular ML, it's very common to have applications that are real time. So you serve your model and then it returns predictions within 200 milliseconds, and so the user is never going to feel it. But then now with LLMs, if you start chaining calls to OpenAI, every call can be half a second. So if you have 10 of them and then you retrieve something from memory, then it starts being 5 seconds. And if you have a real-time application, it will feel like forever. Finally, debugging and actual production behavior, it can be pretty hard to identify what's a bug, even to label what's a bug with LLMs, right? There's more randomness in nature with generative AI, and so it might be hard to understand when it went wrong. While with regular ML code, there's tons of ways in which the program will just crash. Like if you fail, I don't know, your code to the LLM, or input has the wrong shape, or your pre-processing crash, it will crash explicitly so you catch it. And finally, the thing that is hard in production with LLMs is that you likely rely on some APIs, or maybe a foundational model that you downloaded, but you're not going to own the foundational model. And so you're basically enslaved to the person training it or serving it. And usually they have pretty light SLA, so service level agreements. So they don't commit to serving their models under 500 milliseconds or anything like that. It might be the case today, but they don't commit to making it a guarantee in the future. So you might deploy something to production, tomorrow OpenAI is twice as slow, and then that's it. So you have to switch provider. So those are substantial differences. And the rest of my presentation, you can eyeball. It's just I was talking about the patterns that are emerging in terms of the actual stack, all the things that you have to build around the large language model. Some of them have to do with safeguards, like there's large problems with bias potentially, with harmful outputs that you have to try to prevent, but it's hard to control generative models. There's the frameworks, just so that you hear the names. LangChain is kind of dominating this idea of chaining calls to LLMs, tools, memory together. You can even develop visually with LangFlow. And vector databases is a hot topic. And I think, skip that. I had a few slides on when to decide whether you're just gonna prompt engineer, like show the example that you want the large language model to follow just in the prompt, write them in English, versus when you want to fine tune a model or adapt it. But same, I'll probably skip it. Just know that there are many ways to fine tune an LLM efficiently, and it's pretty hard generally to know when you should do it, and it's pretty hard to do as well. And these are the different techniques, just so that you hear them too. Techniques for efficient fine-tuning. When you're fine-tuning like Llama 2 that has 7 billion parameters, you don't want to fine-tune the whole thing, and most of them you don't need to. So you're going to resort to either low-rank adaptation, prompt tuning, or adapters. And it doesn't matter if you're not familiar with them, you can at least look them up. And there are new trends to adapt models dynamically that are fairly complex in terms of ops, but that are emerging. Okay, that was a fast finish. I guess the gist of my presentation is just to show you the different applications, to give you a feel of how those things can start planning, use tools, and use a memory. And also at the end, the part that I skipped quite a bit is what are the new challenges, the new patterns that are emerging in LLM, and also there's quite a bit of disruption or paradigm shift in how you build things with these tools. It's a rapidly evolving landscape, so if you want to try to follow it, it's going to be like drinking from the fire hose. So but I'll be with you on that because I have no idea how to keep up, and I just do my best. Thank you for your attention. I don't know if it's already 29, so I don't know, Victor, if there are closing words or if...
Yeah, do we have any questions from the audience before we close?
Yes. Yes.
So you started off the presentation talking about NPCs in games. So you explained that language agents are what you're mainly working on to formulate the NPC responses and like behavior. Let's say, for example, specifically in Roblox, like if you have a language agent that's based on a generalized language model like GPT-4, would you use like LoRa's, for example, as a layer to like prevent it from giving more generalized responses rather than the specific responses you expect from a game like Roblox? Or what is your methods that you use to like specify the area of responses you want? Like, would you do fine-tuning of the model, or would you use LoRa's as a layer? Or?
Yeah, it's a really good question that we ask ourselves all of the time. So the question is for non-player characters in games, like the use case that I'm working on partly at Roblox. How do you avoid having like very generic behavior, very generic dialogues? Because if you're just using GPT-4, for instance, the API, like, it's not really specialized for Roblox content or for gaming or whatnot. One answer to that is that we're lucky that in the internet there's quite a bit of chatter about Roblox, and probably in the training data set of GPT-4, So we're surprised sometimes by the output that we get, and it's aware of like some terms that are Roblox specific. So in our situation, because it's been around for 20 years at that point, Roblox, and that it's been discussed on the internet, we benefit from the fact that GPT-4 knows about it to a certain extent. But then there's always the question of, there are some tasks like that are very specific. So first, it might be completely overkill to call a large language model. It might cost money, add to the latency, and you might want to skip it. And also, you might want to be more specialized, as you say, and make sure that you're in the right realm. The approach that we are taking is try to build with the API calls first and figure out what you want to specialize, because the more models you add, it's very possible to use what you mentioned, so low-rank adaptation, basically fine-tune a model to your data. It's just that in terms of turning that into a production system, if you have like tens of models that you have to orchestrate, it's pretty hard in terms of just engineering the serving side of things. So we try to be very cognizant of using this approach as rarely as possible, but we have to do that for certain tasks, especially when you're just deciding between a few actions. We even build like just classifiers, right, without a language model for certain tasks. So the reality is not one language model behind it. It's quite a few models. I'll probably take this one, but
Yep. So obviously for like AAA gaming studios, the standards are going to be probably high for implementing such technology. So I was just curious, in your opinion, how far away are we from seeing sort of LLM-driven NPC interactions in large-scale open-world RPGs?
yeah, so it's interesting. So we are getting into more of the gaming world, but there's different approaches. There's large studios, some of them they take a very conservative approach, like Ubisoft. I don't know if you're familiar, it's not the biggest one, but it's fairly big. They just try to create tools for the people developing non-player characters to help them develop faster. It's like suggesting dialogue lines, augmenting the lines with LLMs, very conservative. And then the most innovative side of it, at the other end of the spectrum, it comes more from startup. There's a startup here that is doing very impressive thing called InWorld.ai. I invite you to look them up because they have demos that are very impressive. They had one that the most impressive I've seen so far, unfortunately was taken down for legal reasons, but they built a mod for GTA, Grand Theft Auto, and in which basically the characters were powered by LLMs, and you had to investigate, and it was a very complex investigation. And when you tried it, they were really like, you could tell that they were generative stuff, because when you try to go off-road, they will still stick to the character, but be fairly open to having discussions. So I've already seen fairly impressive demos, and the one company you would want to follow to see, I guess, who's spearheading that is InWorld AI. And I think they might be very close to here, I forget where, but downtown here. So I don't know how far, but if you want to know, I will look at them. You tell me to go when we have stuff. Yeah.
So since, of course, a lot of your work potentially deals with children and younger audiences, have you had any issues with moderating the output of language models if you have any in production, and what approaches are you taking to sort of ensure that everything stays very compliant?
Yeah, thanks. So it's a good question, more specific to Roblox. So Roblox caters to a lot of kids, teenagers, and millions of them, and so moderating content is one of our main topics. And it's like one of those topics that morally we care about it. Also, it can destroy the company if you get it wrong, and of course sometimes it has gone wrong given our scale. And we're working hard. The good thing, where we're lucky is that we have a team who's just focusing on moderating content. So when we're starting with this project, we can outsource all of that to them, meaning that if a non-player character generates a line that's offensive, we will run everything through our filters. We have like these filters that we add to basically every chat interaction, everything, to make sure that at least there's no, insult or anything harmful. Of course, they are not perfect, but at least we're trying. From our perspective, it's mostly centralized. It's something that we have to keep in mind, but we also have like this other layer of protection. And then beyond that, we also think about alignment procedure, which is basically a softer approach, not like a hard filter that block messages or behavior from non-player characters, but examples where you train a model and you show the different outputs that were generated by the same model potentially to humans, and they tell you which one is favorable. If you do that a lot, you end up aligning to the behavior that was directed by the human labelers. And these human labelers can give them guidelines to try to encourage a certain behavior of the large language model. But this one is the soft approach. And in principle, you want to combine both, right? The hard filters to make sure that it doesn't go terribly wrong, the soft approach to make sure that it's as innocuous as possible most of the time. And also we have like specialized behavior and models depending on the age of the players, because we have certain games that you can only play if you're verified as being 17 and older. But it's a big topic and moderation. Sure, thank you. Yes, please.
Okay, so I'm assuming like the language agents that you're working on is more catered towards dialogues from NPCs. What would you say would you say there is an application in like movement for NPCs? Because I've gone over like a few other like reinforcement learning things, like NVIDIA's Calm AI, for example, which is like a reinforcement learning for natural movements of NPC characters or playable characters, for example. Do you think like you'll be working? Are you working on anything regarding movement as well, or is it mostly dialogue based?
Yeah, so we're probably getting close to the limit of what I can disclose, but the question is, yeah, because yeah, in principle, I won't disclose much, but for sure, like most players in that field, we're already like, it's not dialogue focused, it's dialogue and action. So you can think of basically the non-player characters that we're building. They're powered by the large language model that I can either say, okay, write blah, and as a reply to the player, or do this. And then the weird thing is that it can say, I want to do this, and this is not like possible in the world. Like, I don't know, I want to go underwater, there's no water. It happens, and so you have to deal with it. But we're already like most people working on that, we're already trying to deal with both, like dialogues and action. And the big challenge is when you deal with actions, the big challenge that is new is that you have to encode the world in terms of what are the available actions and what is the state of the world. And just like in reinforcement learning, this is usually the main struggle. This is the hard part. Yeah, go ahead. I mean, if anyone has to go, of course, feel free to go. But I'm happy to stay and answer your questions otherwise.
So as far as the language agents go, you said that latency is a huge problem because it takes like a second, for example, for one call. Do you say action calls take longer, or like dialogue calls take longer, or which is?
So yeah, good question. Do action calls take longer than language calls, like replying to users? For sure, action calls are way faster because if you think about it, the latency is going to be actually more than proportional to the number of tokens that you're going to generate. So the more tokens you generate, the longer. So when you generate a reply, it's very long. And the actions are they're encoded. So that means that you just have to generate a few tokens that say go left. So it's much faster. And there's even the option to turn that into a classification problem. So, and the output of the large language model could be called the classifier, because I haven't mentioned that, but tools in language agents can also be other language models.
So please come up and ask your question afterwards. Is there anyone else? Okay, so yeah, please come up afterwards to ask your question one-on-one. And thank you so much. First, thank you.
So first, we'd like a round of applause for our speaker.